So the screen is visible, right? Okay, so let's start this session then. So, good evening, everyone. Myself, Arka Roy. I am working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna, and I will be your NPTEL PMRF TA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, who is a professor in the Department of Electronics and Communication Engineering, IIT Kharagpur. So let's move to the content of today's presentation. So first we'll look around the contents that is basically covered in week 3. And after recapping the contents of week 3, we'll solve the numerical problems which are related to the week 3 quiz. So in week 3, the main theme is basically the Z transform and the rational systems. Rational systems. So far we have talked about the LTI system, and we have also seen the properties of LTI system. We have seen convolution and what is the stability of a system of a signal and all. And in this week, we have been introduced to another kind of system that is called a rational system. So we'll look around what is basically rational system. Basically, we'll have a quick recap of that, and followed by that, when the rational system comes into picture. So associated with that, I guess someone is joining. Okay. So we'll talk about the rational system, and uh, in association with that, when rational system comes into picture, the Z transform in the digital domain, that also comes as a combined effect of the rational system. So in Z transform, we'll see how to, it's basically a special DTFT. We'll see that DTFT is a special form of Z transform. Z transform is more generalized because even if the, yeah, I guess someone is joining. Okay, so those who have joined, so can you just confirm that whether you can see the screen or not?
Yes, screen is visible.
Okay, okay. And so what I was telling is that we'll also talk about Z transform. We'll see that DTFT is a special case of Z transform. Z transform will, in a way, will see that it's a more generalized transformation than DTFT that we have already talked about in the last week. So moving forward with the content of the recapitulation part. So as we have already seen in the content of week 3, it starts with rational system, and more specifically, this is called the constant coefficient equation based system. So in this particular chapter, we'll basically deal with the difference equations. So in difference equation, we'll try to solve the properties of the difference equations, and using the difference equation, how can we form a system? So let us consider we have a signal, input signal, that is xn, and it has basically passed through a system. So currently the system is a black box. We don't know that what is there inside the system, and the output is yn. Now let us consider this particular system is governed by some form of difference equation, and the difference equation is basically given as yn plus a1 y n minus 1, then a2 y n minus 2. Likewise, let us consider ap y n minus p. Okay. And the output and corresponding the delayed version of output is basically related with the input and its delayed versions. So which is equated as b naught xn, then b1 x of n minus 1, b2 x of n minus 2 plus dot dot bq x of n minus q. Now for these kind of systems, this is basically the difference equation. Okay, I guess someone is trying to join. So this is the difference equation system. So the thing is that how can we solve this particular difference equation to get the system representation? So let's try to draw an analogy first. So analog domain signal is basically sampled using some sampler, or let us consider analog to digital converter, and then this converts into digital, or let us not very much specific about whether digital or discrete time. So I am just using the nomenclatures um, roughly. So discrete time signal, then um, uh, uh, for analog systems, we know there is what we call the ODE, that is ordinary differential equation. Differential equation. So in analog system, the difference, we have ordinary differential equation. So the same ordinary differential equation is basically converted as in the digital domain by the ordinary difference equation. That means the main analogy is that in analog domain, what we have the differential equation, for example, d dt of xt plus d dt square of xt equals to, let us consider zt. So this thing we had in case of a analog system. So this system we can actually see in the case of, let us consider an RLC circuit. So if current is going through this path, so I into R, then across this one we have L di dt. That means this is coming in the form of differential equation. So in the analog case, whatever components we have and corresponding equations that we have, so that basically arises the differential equation. However, in the case of digital system, the same differential equation basically converted into the difference equation. So that is basically provided like this. So this sort of equation we can see in case of any digital domain system. Now we can get the next what you call the next index by putting n equals n plus 1, then we can get y of n plus 1, and correspondingly each of these quantities, the index values will be changed, and recursively we can get the values of output at each of the index points. For example, if I know yn, then just by changing n equals to n plus 1, I will get n plus y of n plus 1. And as I know y of n, I will be using this knowledge of yn, and correspondingly recursively, if I solve the equation, I will get all the output values for each of the index points. Now, in the differential equation, we might have seen that, for example, let us consider L di dt equals to, let us say this is k. So any differential equation in the time domain, this has two kind of solutions. One is the transient solution. Another is the steady state solution. So in engineering mathematics, we have this particular thing. One is called the transient, another is called the particular integral. Okay, so this is in terms of engineering mathematics, transient solution is basically called the complementary function. Complementary function. And this one, the steady state solution, is basically called the particular integral. Particular integral. So I'm just drawing some analogy. So in the continuous domain, we have whatever we have as complementary function and particular integral, that is basically same as what is we have as a transient solution and as a steady state solution. So even in circuit theory also, we get to see these kind of problems. So for example, there is a switch, and if I just switch on the device at t equals to 0, then I will have some different response. And if I lead to take draw current or voltage from the particular system, so at t tends to infinite, will be having the steady state solutions. So likewise, whatever we have in the analog domain, that can be used as an analogy towards the digital domain in terms of transient solution and in terms of steady state solution. So to generate the transient solution, for transient solution, we have to consider that xn is in more specific case, xn is 0, and we have some sort of initial conditions. And for steady state solution, the thing is that xn will be there. We have to consider the input, and the thing that we have to take care of, that is the initial condition. Initial condition that should be equals to 0. That means will not allow any initial condition provided that we have some input. However, in case of transient solution, we will consider that we don't have any input. However, we have some kind of initial conditions. So what I mean by this one is, so we'll have like y minus 1, y minus 2, something like that. So these values will exist for transient case. So any difference equation yn will have two parts of solution, ytrn, that is the transient solution, and ysn or yssn, you can say, that is the steady state solution. And how we have to solve the equation, that already I have told. For transient, the equation could be written as like this. yn plus a1 yn minus 1 a2 yn minus 2 dot dot ap yn minus p. Right side will be equals to 0, as we'll consider that the time domain, the input xn is not present, and in more specific case we'll consider that xn is basically switched at n equals to 0. That means all the previous in the left hand side the signal doesn't have any component. So with that, and for the steady state part, this is a more generic solution. So as we have already said that the we need to consider the whole equation to solve the steady state part. A p yn minus p, and sorry, there will be equals p naught xn dot dot b q xn minus q. So we'll consider this whole thing. Now the thing is that we don't we are not able to say that okay, what will be the what will be inside this black box. So now we are at a position to comment about the conditions that what is basically inside this particular box. So for that, transient solution and steady state solution, we have to see that whether the transient part or the steady state part, whether they are linear or not, and time invariant or not. So we need to address these particular questions. So whether both of the system are linear or not, or time invariant or not, so that we are able to answer that what will be field inside this particular box. So in the course itself, so the particular example that we have considered, so let us consider we have a solution, we have a particular difference equation yn equals to yn plus a yn minus 1 is equals to x of n. So let me start with the steady state part. Steady state part. So in case of steady state part, let us consider ysn a ysn minus 1 xn. Now I will first check the linearity property. Linearity is there or not. So to check linearity or not, we know that we'll provide two different inputs at once, and then we'll add the inputs using some linear combination, and we'll see that whether the output is related with the previous summation of the previous inputs when we applied the input separately. So at x when we apply x1n, so the output will be ys1n, then a ys1 n minus 1 and x1 n. So with this, let us consider, and we have some initial conditions that is given ys minus 1 equals to 0. So at n equals to 0, ys1 0, and this one will be 0 as because ys minus 1 is already given that it is 0. So this will be equals to x1 n, x1 of 0. Similarly, ys2 of 0 will be x1 1. Okay, sorry. ys1 1, then x1 1, and a1 ys1 0. So it will be written as x1 1 minus a x1 of 0. Similarly, I can just say that for index 2, it will be x1 2 minus a ys1 1. So it can be further expanded as x1 2 minus a x1 1 minus a square x1 0. Similarly, if I apply x2 of n, and then I can say that y s2 of 0 will be x2 of 0. Likewise, that we have already have seen in the previous case, y s2 of 1, that will be x2 1 minus ax2 naught. Therefore, now if I use the combination of the input, for example, C x1n and C2 x2n, now we have to see that what is the output of the system and whether they are related with the individual summation of the individual output on. Now for this particular case, I can say that ys naught will be C1 x1 naught plus C2 x2 naught, as because the governing equation is this one. With this, I can see that this one is particularly C1 y s1 naught plus C2 by S2 naught. That means that when we apply the signal with a linear combination, the output is ys1 ys of 0, and it is basically related with the combination of the previous inputs, previous outputs when the inputs were applied separately. That means this obeys the superposition principle. Superposition principle. And as because a system which obeys superposition principle, we can say that the system is basically a linear system. So we can comment that the system is linear system. So even you can use the property of induction, and then using the induction theorem also you can prove, for example, you have to choose that for m number of indexes, this is valid. So you have to prove that for m plus 1 also, whatever you have written, that is valid for m plus 1 index. So I have just taken a particular case at n equals to 0, and at n equals to 0 we can see the system is linear. You can take any other examples, for example ys1. There also you'll be able to see that the outputs, the output when we apply the combination of input, that is basically related with the corresponding output summation when the inputs were applied separately. So therefore the steady state solution is basically a linear solution. And we also have to see whether this is time invariant or not. So for example, I am applying something like this. So this is my signal x of n, and I have switched the signal from n equals to 0. That means there is a causal sequence. All the negative on the left hand side, there is there is no component. Now with this, if I apply to the steady state solution system, so I'm writing as SS system. That means a steady state solution system. So in the SS system, when I apply the input, it will act as an output will be similarly, it will have some arbitrary amplitude levels. Let us consider this is amplitude level, and the uh, output sequence will be like this. Now, if I delay the sequence x n minus capital N, and for all the previous inputs, there is no there is no component. So the output system, the output from the state space solution system will also be delayed by the same amount, because in the previous case, for the previous inputs, there was no particular component of that particular input. Therefore, we can see that it basically obeys the delay property. Therefore, as it obeys the delay property, we can comment that the system is time invariant. So if a system is linear and time invariant, so this is the LTI system. LTI system basically follows the convolution property. Therefore, there are several questions you will see that the steady state system, you have to find the impulse response of a steady state system. So let us consider impulse response of a steady state system is HS. and the input is HSN and input is XN, then YN can be find out using the convolution scheme. Convolution scheme. I guess someone is trying to join. Okay. So I can start drawing the inside section. So this is XN and I can consider this as HSN, which has zero initial condition and the output is YSN. Now the steady state part is done. Now we are left with the what you call the transient solution, and output Yn is basically Ysn, that is the steady state solution, and Ytn. And Ytn, we know that Ytn does not depend on the input, however, depends on the initial condition. So from this line itself, we can conclude that even if we don't provide any input, let us consider at n equals to 0, there is no component of the input. Still, as there are the previous initial conditions are already available, it will provide some output. That means Ytn will have some particular value, even if the input is not present. Therefore, we can consider that the system is time varying. Time varying. So we'll have an adder and we'll have initial conditions. However, there will be no effect of xn, so we'll not add any line coming from xn, and this is basically the yt of n, and when we add these two, we'll get the output. So this is basically the representation of a any rational system with basically the constant coefficient difference equation system. So with this, we have seen that this particular system, the steady state system, has got the property of LTI system, and this particular system is not this is not an LTI system. This time varying system. Now we'll have a quick look on Z transform. So Z transform, if we have a signal Xn, the sample signal Xn, so we'll can define the Z transform as X of Z as summation in varying from minus infinite to infinite Xn Z to the power minus n. So this is basically the Z transform. Now if I put Z equals to, now Z we know this is a complex variable, and Z in basic complex algebra we write Z as e to the power I theta. So in this particular case, let us consider we have a special condition when r equals to omega and theta will replace it with the variable omega, that is the uh, digital frequency variable. Frequency variable. So with this particular condition, Z will be reduced to e to the power I omega. So I can replace this as, let us consider Z equals to e to the power I omega. Then it will be reduced as xn, n varying from minus infinite to infinite, e to the power minus j omega n, j or I, whatever. These are complex term only. So this basically the DTFT. So we can say DTFT of Xn is equivalent to Z transform of Xn evaluated at Z equals to e to the power j omega. So in this way, we have proved that the DTFT is a special condition of Z transform, and in a way, we'll see one particular example where DTFT does not exist. However, with some proper value of R, so this R is basically this one. So with the proper value of R, we can still have the Z transform converging. So we'll see that example shortly. For example, Xn, we can consider a particular sequence that is Xn is equals to 2 to the power n un. So 2 to the power n un, this is our right-sided sequence. So it will start with 1, then 2, then 4, and this is a growing sequence. So if I start taking the summation of Xn varying from minus infinite to infinite, so effectively this will reduce from 0 to infinity because in the left hand side there is no component. So it will be 1 plus 2 plus 4 plus dot 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 infinity. So this is an infinite GP series, and you can see that if we start adding all these values, this thing will not converge. And in this particular case also, DTFT is not existing. We can show some demonstration. For example, x e power j omega is xn e to the power minus j omega n, e to the power minus j omega n. So, and n is varying from minus infinite to infinite. To get it stabilized, the summation of the mod of summation of this should be less than infinity. And I can say that xn and e to the power minus j omega n should be less than infinity. And I can say that summation of xn, so mod of e to the power j omega n, any value of e to the power j omega n, if we take mod, that will be equals to 1. So summation of xn should be less than infinity so that I can get the DTFT stabilized. So for this particular case, as the summation is not converging, therefore this particular equation, this particular condition is not valid. Therefore, the DTFT will not exist. So with this particular application, we can see that the DTFT of this particular sequence is not converging, but still with the proper choice of R, we can still have the Z transform to be existing. So now we'll see the Z transform case. So x of z is summation xn z to the power minus n, and I can write 2 to the power n un z to the power minus n. So just erase this one. Okay. And n will vary from 0 to infinity, as because we are dealing with the right sided sequence 2 to the power n z to the power minus n equals to 0 to infinity. Now we have to see the stability here also. So this will be mod of 2 to the power n z to the power minus n. And I can write this as 2 to the power n z is equals to r e power j omega. So it will be r to the power n and e to the power minus j omega n, and then take a mod. Then mod of summation will be summation of the individual mods. So the summation, the mod will go inside. So 2 to the power n, r to the power n, e to the power minus j omega n. Now, uh, these are multiplicative with each other. So mod of any multiplicative sequence will be mod of each of the particular sequence. So I can write it as summation 2 to the power n, r to the power n, and this will be equal to 1 as because e to the power minus j omega n, if we take a mod of this will effectively reduce to 1. Therefore, uh, this will be r to the power minus n as because it was z to the power minus n. So I can write it like this: 2 divided by r whole to the power n. And as because these two are particularly, r is basically a number and 2 to the power n, this will also yield a number. So mod of that particular number will be the same thing. So I have removed the mod. Now, so I can see that this summation to basically converge the sum. So it should be less than infinity. Therefore, the Z transform will exist, and we have to converge the sum. So let us consider a particular example. Let us consider r equals to let us consider 4. So it will be 2 to the power 4 whole to the power n summation. So it will be half to the power n. So if I consider, and n is starting from 0 to infinity, as because we had previously see that this is a right-sided sequence. So I can write half to the power 0, then half to the power 1, then 1 by 4, then this will be 1 by 8 like this. Therefore, we can see 1 plus half plus 1 by 4, 1 by 8. This is also an infinite ZP series, and the common ratio. So the common ratio is half, which is less than 1. Therefore, I can say that the summation will converge. However, if I consider r is equals to 1, then the summation will effectively reduce to 2 to the power n. That means it will start from 1, 2, 4, dot, dot, dot. Therefore, we can see this will not non-converging sum. So the condition we can take as r should be greater than 2. So for those particular condition, if I consider r is greater than 2, so we can see that the summation will start converging, and as the summation will converge, this summation will effectively reduce to some particular value which is less than infinity. Therefore, the Z transform will exist. So we have seen that even if the DTFT was not existing for this particular sequence, the Z transform can exist with the proper choice of R. Okay. And with Z transform, we have to also very careful about the ROC, that is called the region of convergence. That means the Z transform. So here we have seen that analytically, if we just find the Z transform, Z transform of a particular sequence, and we'll get some particular representation of the XZ, still will not be able to say that whether the sequence, whether the Z transform that is for this particular sequence, whether it is converging or not. So for that, we have something called region of convergence, and in many cases we'll see that several sequences will have same particular Z transform representation, Z transform output, but still the question is that whether for all these particular sequences, the ROCs are same or not. So determining the region of convergence is one of the trivial problem in case of Z transform. So we have to be very careful about that. So I will just take some basic sequences, and then I will show that how the region of convergence can be considered. So let us consider a very generic example of a right-sided, strictly right-sided sequence. For example, it will start from n equals to 0 and this is going up to infinity. And this is basically xn. So xz for this particular sequence will be n equals to minus infinity to infinity, xn, and then z to the power minus n. Now n will vary from 0 to infinity as because we already have seen that the sequence has no component in the left hand side. So xn z to the power minus n. Okay, good enough. Then I can write x0 z to the power 0, then x1 z to the power minus 1, x2 z to the power minus 2, likewise. So this is x sub z. So I can write it like this. X of 0 1 by z to the power 0. Okay. Now this is basically the Z transform equation. Now we have to see whether the Z transform is stabilized or not. So we'll see that mod of xz. So summation, it will be x of n z to the power minus n, and n will start from minus infinity to infinity, effectively reduce, and there will be a mod over here. And we have seen that I can write z to the power n as r to the power minus n, e to the power minus j omega n. Then there will be a mod, and I can write it as like this: mod of xn multiplied with r to the power minus n, r to the power minus n, yes, and e to the power minus j omega n. This will effectively there will be, if we take mod, that will be reduced to 1. Now I can write this particular thing as x of n dot 1 by r to the power n. Now if I choose, now this is the z plane, z plane. Now this is the real axis and this is the imaginary axis. Now real axis and imaginary axis, this will basically create the contours. So for a particular z, I will be having some set of contours, and there will be a particular contour that will be for z equals to 1 into e to the power j omega. So this will be called as unit circle. So let us consider this is the unit circle. So for this case, R, let us consider R is 2. So this summation will, and this thing is, will consider this thing is also converging. So this is converging, and if I take R equals to 2, so this whole thing, whole summation will converge. Likewise, if I take R equals to any big value of R, if we take, so for that particular case, the summation will converge. For example, if I take the limiting case, R tends to infinity, 1 by infinity will be 0 and the summation result will be 0. Therefore, the summation is converging. That means still for R equals to infinity also, the summation is basically converging. Now, what is the limiting case for which the summation is not converging? That is R equals to 0. So if I put R equals to 0 over here, so 1 by 0 will raise to infinity. That means it is overshooting the summation is overshooting the limiting case, and therefore the Z transform will not exist for R equals to 0. That means in the Z plane at 0 point will not have any ROC, valid ROC. And after this 0 point, for any of the value, will have the ROC extended to infinity point. And as basically the ROC is enclosing the Z equals to 1, that means unit circle, we can say that this is stable. And there is one another observation for right-sided sequence. We can see the ROC is diverging in nature or outside going. That means we can see that all the ROC is going outside, dispersing from any R equals to 0 and going to infinity. Similarly, I'm not considering the case for the negative side negative side part, negative side sequence. So for that particular sequence, we'll see that R equals to infinity, then R equals to infinity is the limiting case. We'll not consider the R equals to infinity part. So I'm just crossing this thing. So we'll not consider this thing. However, the ROC will effectively lead to the converging nature. That means it will come in the inward direction. That means for the note is that for left sided sequence, ROC is converging shape or it is inward going shape. So with this, we have almost covered the basic concepts that professor has already talked about in the 5 lectures. So this was the quick recap part, and with this we'll start solving some numerical questions which will be helpful for the week 3 quiz. So starting with the first question. So the question states that we have a particular sequence xn as a to the power minus n u of minus n. Now we need to find the Z transform and associated ROC. So how can we proceed? So I can write xz as summation n equals to minus infinity to infinity x of n z to the power minus n. So can you tell me whether the sequence is right-sided or left-sided sequence?
Left sided.
Yeah, this is a left-sided sequence. So it will start from a to the power minus n. Let's consider at n equals to 0. So we'll consider this 1, and in the left side it will like this. Okay, and I don't know that what is the value of n, so that I will not be able to comment on the shape of the original sequence, that how it basically looks. Depending on whether a is greater than 1 or a is less than 1, the sequence shape will change. But the thing is that these are left-sided sequence, that is for sure. Now I can write it as n equals to 0 to minus infinity. That means I am summing from this side to this side, and already we have already talked about this particular case, that summing the signal from this way to this way or this way to this way, this will effectively end up to same result. So x of n z to the power minus n. Now let me write the sequence a to the power minus n, and already we have uh, taken care of the u of minus n by putting the proper limit ranges. So this will be z to the power minus n. Okay. So n equals to 0 to minus infinity. So I can write it like this. I can break the summation as for n equals still I can make some more modifications. N equals to 0 to minus infinity. Then 1 plus az to the power minus 1, az to the power minus 2 dot dot to infinity. And to make the summation converging, so this is an infinite GP series. To make the summation converging, the common ratio, this is very much important. In each and every Z transform question, you will see the same thing. So the common ratio should be less than 1. Therefore, the common ratio is AZ. So I can write that AZ to the power minus 1. So this should be less than 1. Okay. So with this, so mod of common ratio. So this I can write it like this. So 1 divided by 1 minus. So still I can comment it like this. 1 divided 1 plus 1 upon z 1 upon z square like this. This I'm making some mistake. Okay, yes. I had made some mistake. So what is the mistake? That is the power was minus n and I am going from 0 to minus infinity. So when I am going to 0 to minus infinity, the range is like 0, minus 1, minus 2, dot minus infinity. That means for 0, this is 1. Okay. So for n equals to minus 1, this will be az to the power plus 1, as because we are taking n equals to minus 1. So minus 1 into minus, so that will effectively lead to plus. So this will be az square like this. So therefore, the summation output will be 1 divided by 1 minus az, as because the common ratio is now az. And the common ratio mod should be less than 1 so that the summation will be existing. Therefore, we can write that z mod z equals to 1 upon mod a. So this is the ROC condition. So from the common ratio, mod of common ratio less than 1, the ROC thing will come and the summation result will show the Z transform output. So these two are the components of the result. So option C. So moving forward with the next question. So next question basically tells that there is a sequence x of n, which is a to the power n u of n plus b to the power n u of n. So this is a summation of two sequences, and where un is the unit step sequence, and it has been written that so this is the condition given, and we need to find the ROC of the Z transform of xn. So let me just write some property. Un Z transform. So let us first formulate the properties. So you can use the properties, otherwise you can, if you don't remember the properties, we can start by solving the equation first. Let us consider x cap of n is a to the power n un. So x cap of z will be x cap of n z to the power minus n, and n will be from minus infinity to infinity. Now, if I put this one as a to the power n u of n z to the power minus n, so n will be from 0 to infinity, because we are now dealing with a right-sided sequence. So I can write it as a to the power n z to the power minus n, and n equals to 0 to infinity. Therefore, I can further reduce this particular sequence as z divided by a to the power minus n, and n is running from 0 to infinity. So it will be like 1 divided by z by a to the power minus 1, z by a to the power minus 2, dot 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 dot. So the summation will be 1 minus z by a inverse, or I can write it like that, 1 minus uh, a z inverse. Okay. So this is the Z transform, and I need to find the associated ROC also. So the associated ROC will be Z by A to the power minus 1 mod should be less than 1. So I can write it like uh, A Z inverse less than 1. So this I can further write it like Z to the power minus 1. So a by z minus 1. So I can just z by a should be greater than 1. So mod z should be greater than mod a. So this is the ROC of this particular first sequence. And as because this is an uh, right-sided sequence, and let us consider this is the uh, point A. So the ROC will go out of so ROC will go out like this, and this has already given that the information is like this, and A is less than 1. So unit circle is enclosed. So let us consider this is the unit circle. This will be outside that position, and unit circle is enclosed with the what you call the ROC. So similarly, so a to the power n un, this has a ROC like a, and b to the power n un, this will have an ROC. Let me just draw it over here. So it has been already told that b is greater than a. So b will come over here. This is b, and the unit circle. This is the unit circle. So individual ROC, now if I consider individual ROC, this one is going out like this. For the second one, the ROC is also outwards, as because second signal is also an right side. So ROC is a converging shaped ROC, sorry, diverging shaped ROC. Now we are taking summation of these two particular sequences. So as per the property, x cap n and x2 cap n, if these two sequences are added, so common ROC, so ROC, let us consider ROC effective should be ROC1, sorry, ROC1 intersection ROC2. That means we have to find a common ROC point. So the common ROC point will be this one, this region. That means so the ROC should be uh, mod z greater than mod b, as because mod for mod z greater than mod b, this is the common ROC point. So let's see the options. So it will be option B. That means we have added initially two particular sequences, and we know that ROC ROC effective should be ROC1 intersection ROC2. So we have initially found out the what is the ROC for this particular part. Then we have found out ROC for this particular part, which is like this. And then we have found that the final effective ROC for the common sequence or the added sequence. Moving forward with the next question, the xn is represented as xn delta n minus 3, then 2 into delta n minus 5, and we need to find xz. So let's first find the z transform of delta n. So xz, let us consider x cap of n is delta n. So I can write delta n z to the power minus n equals to minus infinity to infinity, and delta n is multiplied with z to the power minus n. So any sequence multiplied with delta that will be evaluated as that particular sequence evaluated with n equals to 0, as because at n equals to 0 that delta is existing. So minus infinity to infinity delta n into 1, n equals to minus infinity to infinity. And if I sum the delta n over minus infinity to infinity, I will get 1. That means delta n will have z transform equals to 1. And if I have delta of n minus k for that particular thing, if I let us consider x cap n is now delta n minus k, for that particular case, the z transform will look like delta n minus k z to the power minus n, k equals to minus infinity, sorry, n equals to minus infinity to infinity. Now this will be delta n minus k z to the power n minus k, as because it has to be evaluated at that particular location. Now the summation is minus infinity to infinity, and I can write that delta n minus k z to the power minus n z to the power k, and if I write n minus k is equals to, let's say, m. So n is equals to minus infinity to infinity. So if I change the variable with m, so this will be changed with m, and here n will come as m plus k. So m plus k, and there will be another z to the power k, and we can say that delta m evaluated at that particular location, and there is a summation that will effectively lead to 1, and 1 z to the power minus k will be out from the system. So I can say that this will be effectively uh, z to the power minus k into z transform of delta n. So this will be z to the power minus k into 1. So the main thing is that if xn has z transform xz, so xn minus k left shift will have z to the power minus k xz. So this is the main property, or this is the time shifting property. Now we need to find the what you call, I need one more page for this. Okay, so we need to find the xz first. So xz could be z to the power minus 3 into 1 plus 2 into z to the power minus 5. Okay. Now the question states that we have y of z is x of minus z. So we got xz as z to the power minus 3, 2 into z to the power minus 5. Now we need to find x of minus z. So x of minus z will be minus z whole power minus 3, 2 into minus z whole power minus 5. So x of minus z will be minus z to the power minus 3 minus 2z to the power minus 5, as because we have odd powers. Therefore, I can take minus out and z to the power minus 3 plus 2 z power minus 5. So yz is equals to x of minus z, which is effectively as z to the power minus 3 to z power minus 5. So I can write minus of xz. That means yn, if I take inverse transform of inverse z transform, so yn will be minus of xn. So this is the final answer. Yn is x of minus of xn, sorry. So not option. Okay, so option D, yn is minus of xn. So the next question is that the poles of the system for the discrete time system shown in the figure, the poles of the transfer functions are located at these particular location. So this is a feedback system. So this particular feedback system has given some gains and some delays, and we need to find the transfer function of the system so that we can get the poles location of the poles. So we need to deal with some difference equation, as because already we have seen that rational system, this is a rational system configuration. For the rational system configuration, we have to have some kind of difference equation. So let me convert this whole thing into Z transform format. So as because the delays are given in terms of Z transform only. So xn will have Z transform of xz and yn will have Z transform of yz. So we can configure that at this particular location, the output is xz plus y is coming and there are two delays. So z to the power minus 2 multiplied with minus 1 upon 6 yz. Okay. So this is the output at this particular location. Now this output is added with this particular thing that is coming over here. So this thing will be added with y of z to the power minus 1, because here is only single delay is there, and then the signal is going through this particular block with a gain of 5/6. So 5/6, and this is the output. This is the total output after second adder. Now this thing is equated with yn. That means the whole thing will be equated with yz, as because the output is yn. So let me just writing it again. So yz xz z to the power minus 2 into so let me write it like this, xz minus 1 upon 6 z to the power minus 2 yz plus 5/6 yz z to the power minus 1. So I can take all the things in left hand side. So it will be 1/6 z squared plus 5/6 z, and this is xz. So I can still reduce it as yz, then I can take 6z squared as common, and then it will be 6z squared plus 1 plus 5z. So this is xz. I guess I made some mistake. So this will be minus. So this will be minus, and same thing over here. So yz by xz is effectively 6z square divided by 6z square minus 5z plus 1. So now if I let me just copy this thing in the next page. So this is effectively the transfer function. Now the transfer function, I need to get the poles. So denominator will be equated with 0. 6z square minus 5z plus 1 is equals to 0. So if I equate this, so I will get 6z square minus 3z minus 2z plus 1 is 0. So I can take common 3z. 2z minus 1 minus 1. 2z minus 1 is equals to 0. So 2z minus 1 and 3z minus 1 is equals to 0. So the poles location will be half and 1 by 3 respectively. So option C. So poles are located at half and 1 by 3. So the next question states that there is a difference equation. So the difference equation is given as yn is equals to 1/3 yn minus 1 plus xn, with an initial condition given as y of minus 1 is 2. Find the general response. So we need to find yn as general response for n greater equals to 0. So we need to see that the given equation is a difference equation and we are told to find the general response. That means we need to find the general solution of this particular difference equation. So as already we have discussed that any difference equation will have two parts of solution. One is the transient solution and one is the steady state solution. So we need to find these two solutions separately so that we can get the what you call the general solution. So let me start with solving the transient part. Transient solution. So ytr 0 will be, I'm just putting the indexes over here. So ytr 0 will be 1 upon 3 y of minus 1 and x of 0. So it will be 2 by 3 plus 0. So let us consider. So if there is nothing mentioned over here, so we'll consider that. Let us consider that xn is 0 for all n less than 0. That means xn is a right-sided sequence. So with this, the output is 2 by 3. ytr1, it will be 1/3 ytr 0 plus 0 as because okay, uh, for transient case x of n is equals to 0, as because for the transient case we don't consider the input, so that will be 0, and 1 upon 3 it will be multiplied with 2 by 3, so 2 by 3 square. Now ytr at 2, it will be 1 upon 3 ytr at 1, therefore 1 upon 3 into 2 by 3 square. So 2 by 3 q. So we can see there is a pattern is coming. That means ytrn is equals to 2 by 3 n plus 1. Is it not? So for index 1, so the power of 3 is 2. For index 2, power of 3 is 1. That means it is incremented by 1. So this is the first general solution for the transient case. So 2 by 3 whole to the power minus n plus 1. Now we need to get the solution for the what you call the steady state part. Now steady state, for steady state system, we will consider that steady state solution is linear, time invariant system. So as because this is an LTI system, so this will follow the convolution scheme. Convolution scheme. So we can consider that given xn, to get yssn, that is the steady state solution, there will be some transfer function hssn, and yssn is basically the convolution between these two xn. Now given the system, so given system, oh, sorry, so let me just copy this thing. So given is that yn is this one. So if I take z transform in both the side, so it will be 1 upon 3 z to the power minus n yz and x sub z. And for steady state case, we already have told that initial conditions ICs are 0, will not have any initial condition. Therefore, if I take yz common, so 1 upon 3 z inverse is equals to xz. So hz is effectively yz divided by xz. So that is 1 divided by 1 upon 3 z inverse. So we know that a to the power n un has this particular sequence 1 by a z inverse. That means this is falling into the same category. Therefore, I can consider that HSSN, this is HSSN, is the inverse z transform of this particular thing. So this will effectively reduce to 1 by 3 whole to the power n un. And already, as because I told initially itself that if it is not given anything, any particular comment, so we'll consider that xn is 0 for all negative indices. So effectively, we have landed to the same thing, that this is a right-sided sequence and all values for the negative indices are 0. Therefore, yssn, we already have told that it is convolution between these two sequences. So I can say the convolution will be 1 upon 3 n minus k un minus k xk, and k is varying from minus infinite to infinite. Therefore, the steady state solution is looking like this, and we already have got the transient solution. So full solution y total n is y transient n and y steady state n. So the transient n is 2, 3 to the power n plus 1 plus summation k equals to minus infinity to infinity 1 upon 3 n minus k u of n minus k and xk. So this is the final result. So let me just check with the given solutions. Oh, so another thing we can consider that as because it is a right-sided sequence, we can consider the minus infinity to be reduced to 0 as because we are dealing with the right-sided sequence. So let me just check. So this is wrong. This one is wrong as because the transient solutions are wrong. And this is fine. Yeah. So this will be the thing that 1 by 3 to the power n minus k, and un minus k we can consider this as 1 because for each and every case there will be unit sample of 1 as because we know that un sequence looks like this. If this is un, all values are 1. So multiplying with un or un minus k is effectively meaning that we are multiplying each sample with the amplitude value of 1. So we can effectively reduce the thing into 1 by 3 whole to the power n minus k multiplied with xk. So the final answer is option D. So the next question states that given xz is z to the power minus n 1 minus 3 z to the power n. Now the main intriguing part is that ROC is given as z, mod z is 3 or mod 3 or whatever. So we already have seen that a to the power n un, it has the z transform is as this, which looks like I can consider z to the power minus n multiplied with 1 minus 3 z to the power minus 1. So this is just a delay multiplied with the z transform of some sequence. So I can see that these z transforms are looking alike. Just in place of a there is 3, but we need to consider that ROC also. So for this particular case, ROC is mod z is greater than mod a. That means the ROC is different, and that is why the question is so important that they have given the ROC, and the ROC is differing from the ROC of a to the power n un. That means even if the z transform looks alike, the ROCs are different. Therefore, I cannot write this is an inverse z transform of a to the power n un. So we'll see that what could be the possible solution for this sequence and with this particular ROC. Okay, so let me take a dummy sequence x hat n as a to the power n u of minus n minus 1. So u of minus n minus 1 will look like u of minus n minus 1. So in first week's live session, I told you that if any transformation is given in any particular signal, we'll look from this side and then we'll start drawing. So let us start with un. Un looks like this. This is simple un. Now we are delaying the signal by an amount of 1. That means the signal will start from index number 1. This is u n minus 1. Now what we have given minus n, that means it is time reversal or sample reversal. So the samples will look like minus 1. So it was starting from 1 to 3 dot 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 dot. So the same thing will just be reversed around about the y-axis. So minus 1, minus 3 dot 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 dot. So this is your final u of n minus n minus 1. So this is how the signals looks like u of minus n minus 1. Now I need to find the z transform of this particular sequence. So a to the power n u minus n minus 1 z to the power minus n. Now the limit of n will be crucial. So it will start from minus 1 and it will end to minus infinity as because this is a left sided sequence. Okay. Now let me write it in a more compact form minus 1 minus infinity And I can even write it like z divided by a to the power minus n starting from minus n to infinity, and I can write it z by a. Now n is taking minus value, so this will effectively get a positive value in the power. So z by a whole square, z by a cube dot 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 dot. So I can take z by a common, and then 1 plus z by a whole square, and then this is again an infinite GP series. So if I take one more page, yeah, so I can write it like this. So x cap z is 1 is z by a divided by 1 minus z by a, as because z by a I have taken out. So this thing will be 1 divided by 1 minus z by a multiplied with z by a. So here I have taken the whole z by a thing in the numerator part. So if I reduce this, it will be 1 divided by a z inverse minus 1. That means if a to the power n u minus n minus 1 is given to you, the z transform will look like a z to the power minus 1 minus 1. Okay. Now, if I just multiply minus with this minus and minus 1, it will be 1 minus az inverse. And the intriguing thing is that now we need to find the ROC. So the ROC is, we already had told you, common ratio mod should be less than 1. So mod z by a should be less than 1 because the common ratio was z by a. So mod z by a should be less than 1. So mod z should be less than n. Now it is looking like the same thing, that mod z is less than a particular value and the z transform is also looking alike. So I can start solving this particular thing. So xz is z inverse 1 minus 3z inverse. That means there is some sequence and a delay is multiplied with that. So if I take z transform of this particular thing, it will be minus 3 to the power n u of minus n minus 1. Okay. Now I have multiplied a delay with that. So x of n minus 1 will have z to the power minus n xz. That means all the indices over here which are present, that will be replaced by n minus 1. That means the delayed version, the whole thing, if I consider right now, the whole thing will have minus 3 n minus 1 u minus n minus 1 minus 1. That means minus 3 to the power n minus 1 u minus n plus 1 minus 1. That means the final result will be minus 3 n minus 1 u of minus n. So the option C. Okay. So moving forward with the next question. So there is given that Hn is z inverse of h of z, and this is stable. No, we have to find Hn given the z transform of that particular sequence. So I can write Hz as 1 6z 1 minus z inverse. So 1 divided by 6z square plus z minus 1 So this is, and Z will go up. So okay, let me just solve it in a different way. So in case of Z transform questions, if we have to solve the inverse Z transform, what is the common practice? Common practice is to divide with the some factor which is same as the Z factor. So the Z factor is over here 6Z. So we'll be dividing this thing with 1 upon 6Z. So this will be 1 upon 6 Z inverse divided by 1 plus 1 upon 6 Z inverse, then 1 upon 6 Z to the power minus 2. Now this thing could be written as 1 by 6 Z inverse, and then I can factorize this particular thing 1 by 1 upon 2 Z inverse and 1 minus 1 upon 3 Z inverse. Okay. Now the thing is that we have got the transfer function in a more compact form. So we need to still rationalize these two, this whole thing. So for rationalization, let us consider this is A by 1 plus half Z inverse plus B 1 minus 1 upon 3 Z inverse. Now I can write that from equation 2 and equation 1, I can write that 1 by 6 Z inverse, it will be A into 1 minus 1 upon 3 Z inverse plus B multiplied with 1 plus 1 upon 2 Z inverse. Now we need to find what is the value of A and what is the value of B. So to find the value of A will be h of Z multiplied with the corresponding pole. So it will be multiplied with 1 by multiplied with 1 minus 1 upon 3 Z inverse and evaluated at corresponding pole location. So the pole locations are 1 minus 1 upon 3 Z equals to 0. So Z equals to 1 upon 3 and second pole is Z equals to half. So this should be evaluated at Z equals to 1 by 3. So hz is this thing. Now if I multiply it with this particular factor, so this will cancel, these two will cancel. So 1 by 6 and this is 3. So 1 plus half multiplied with 3. So this will be half and there it will be 5 by 2. So 1 upon 5. So A is 1 by 5. Now we need to find similarly what is the value of B. So B is hz multiplied with 1 plus half Z inverse and so here the pole will be Z equals to minus 1 by 2 as because there is a plus sign over here. So Z equals to minus half. Now if I multiply the thing, so 1 by 6 multiplied with minus 2 divided by 1 minus 1 upon 3 divided with minus 2. So it will be minus 1 upon 3 divided by minus minus, it will be get plus. So 3 plus 2, 5 by 3. So it will be minus 1 by 5. So B is minus 1 by 5. So I can write hz as A divided by, sorry, A divided by, let me just copy this part. And paste this thing to So let me just put the values over here. So it will be 1 by 5 is 1 upon 5, 1 plus half z inverse, and this is minus 1 by 5 multiplied with 1 divided by 1 minus 1 upon 3 z inverse. Now I need to find the inverse transform. So this is 1 by 5, and this the question in the question that it has been told that this is a stable system. So stable system means it should enclose the unit circle. So and they have been given a transfer function. So the transfer function, in any transfer function, we'll consider the transfer function is causal. It comes from a causal sequence. Therefore, this will be 1 by 5 multiplied with 1 upon 2 whole to the power n un minus 1 by 5 minus 1 by 3 whole to the power n un. So this is the solution. So let me see the answers. So this is, oh sorry. So the a to the power n un has the solution as a z to the power minus 1. So likewise, this will be plus and this will be minus. So this will be 1 by 5 un, and I guess there is some plus minus mistake has been happened over here. So this is 1 by 5, 1 by 3 un, and b is, so 1 by 5. I guess there is some mistake has been happening, plus and minus. So this will be 1 minus 3 by 2. And okay.
Sir, second term is
So,
positive. You have taken it as a negative.
okay, yes. Second term is positive. So
Yes.
the thing is that b will be 1 by 5 plus, and this will be, a will be negative. Yes. So in this way, I just have, I guess, taken the signs opposite. So this particular thing will be minus. So I guess this is fine, right? Is this okay? Hello? So this is actually option C. So in the next question, we have yz is equals to xz, and we have taken mod square. So we need to find yn. This is the question. So this is a very simple question. Can you tell me that which of the options is the correct one? So you can just think it like this. Xz xz. So you can think it like this. Anyone, which one of these options seem to be correct. So let me give you a hint. In time domain or in the sample domain, if there are two sequences x1n and x2n convolved, then in the Z transform domain, it will be multiplied x1z into x2z. So with this concept, if I just take the inverse over here, so I can see that these things are multiplied with each other, and the exit part xn is in the question. I have not written it over here. Xn was real. So in the last class also we had seen that if xn is even and real, so in the question it was written that xn is even. So if xn is even in the DTFT domain, it will be just the magnitude part. There will be no phase. So similarly over here, we only have the magnitude part. That means we are just taking the convolution between same sequence. So convolution between same sequence will effectively give you xz multiplied with xz. And as because the signal is even, so the DTFT domain or Z transform domain, they will have only the magnitude part. That means xz whole square. Therefore, the answer is xn convolved with, this is a convolution operation. So xn convolved with xn. So this will lead to the uh, this particular Z transform representation. Okay. So the next question is xz is equals to 3 divided by z minus 2 with an ROC z greater than 2. Now I can write it like this, xz 3. Let me just divide it with z. So 1 minus 2z inverse. And we already have seen a to the power n un will have 1 minus a z inverse with the ROC mod z greater than mod a. So this particular thing is matching with this. So if I just take, if I factorize these two as like this factor multiplied with z inverse, so this one will have the z inverse z transform of 2 to the power n un. Okay. Now we are we are multiplying a delay with this particular sequence. Let us consider this x hat n. Now we are adding some delay over here. So xn will be x hat n minus 1. So everything will be shifted by 1 unit in the right side. So n will be replaced by n minus 1. So 3 into 2 to the power n minus 1 into u of n minus 1. So this is the final output, and the output is same as option D. Now this is determine the initial value. So initial value means x n evaluated at n equals to 0. This is called initial value. Now we have been given a Z transform. So apparently it looks like that we need to find the xn, and then we'll be evaluating this thing in evaluating the thing at n equals to 0. But this will be quite cumbersome. So there is a particular theorem is there that is called initial value theorem. So I can just write it like this: x0 is limiting condition at z tends to infinity xz. Now the question is how I have got into that particular relation. Let me just prove the relation for you. So xz can be written as xn z to the power minus n, and n is running from minus infinite to infinite. Now we'll consider again that the system is causal system. So causal system means my limit will be restricted from n equals to 0 to infinity x of n z to the power minus n. Okay, so x0 plus x1 z to the power minus 1, x2 z to the power minus 2 dot dot, and it will run till infinity. So I can write it as x0 x1 by z x2 by z squared likewise. Now if I take limit both side with z tending to infinity, so I will get x0 as it is. And all these terms, if we put infinity in the denominator, so all these terms will be reduced to 0. Therefore, we can get that limit z tends to infinity xz is actually x naught. That means this is the initial value theorem. Same as there is another theorem that is called the final value theorem. So that is called final value theorem. So final value theorem is like I need to find x n at n equals to infinity. So I will take limit z tending to 1 z minus 1 into xz. So likewise, you can check the proof. So this is a very standard proof. For example, we just have to take the z transform and multiply with z minus 1, and then we need to take a limit. So this is very easy to prove. So if I take the z transform, so this is 2z z minus 5 by 12, and then z minus half and z minus 1 by 3. So I need to find limit z tending to infinity xz. So limit z tending to infinity 2z z minus 5 by 12 divided by z minus half z minus 1 upon 3. So if I directly put infinity, this will be infinite by infinite L'Hospital relation. So I can multiply 1 by z squared in both numerator and denominator. So it will effectively reduce to limit z tending to infinity. 2, this will be 1z will cancel this one, and second z will 1 minus 5 by 12z. And here also I make the z as 1z will go over here, 1z will go over here. So it will be 1 minus 1 by 2z, 1 minus 1 by 3z. Okay. Now if I put z equals to infinity, this will be 2, 1 minus 0, and in denominator 1 minus 0, 1 minus 0. So output is 2. That means limit z tending to infinity xz is equals to xn evaluated at n equals to 0 or x of 0, the value is 2. So this is the final answer. So find the system function hz. I guess I have not written the question properly. Okay, so this question xz is given 2 minus 3 by 4 z inverse divided by 1 minus 3 by 4 z inverse 1 upon 8 z to the power minus 2. Now there are four statements. Sorry, there are three statements, and the options are given that which of the statements are valid. So we need to find the poles first. So let me just write it like this: 2 minus 3 by 4 z inverse, and this I can write is 1 by 3 and 1 by z square. So I'm not bothered about the numerator. Let us consider it is nz. So this will be 8z square, 8z square minus 3 to the 6z plus 1, and this is nz, and this will go up. So 8z square will be multiplied in the numerator. So this is multiplied in the numerator, and let me find the poles then. So this will be dz is equals to 0. So 8z square minus 6z plus 1 equals to 0. So 8z square minus 4z minus 2z plus 1 is equals to 0. 4z, 2z minus 1, and then minus 1, 2z minus 1 is equals to 0. So 2z minus 1 and 4z minus 1 is equals to 0. So our poles are at half and 1 upon 4. Okay. So poles are at 1 upon 4, 1 upon half. So let me just draw the circles. And let us consider the unit circle is this one. This is the unit circle. So I have to read the statements. Consider the following statements. The system is stable and causal for z mod z greater than half. So let us consider statement 1 is mod z greater than half. So mod z greater than half means this is the ROC, and this is indeed causal, and uh, this is actually stable too. Then the system is stable but not causal for z less than 1 by 4. So statement 2 is mod z less than 1 by 4. It is stated that the system is stable and not causal. So not causal, it is okay. That means this is coming inward. So not causal, it is okay. That means it has some left sided part. So that, therefore the ROC is converging in nature or inward in nature. But the thing is that they have written there is stability. So stability, it is not correct because it is not enclosing the unit circle. That means statement 2 is incorrect. So the third statement is what? Third statement is the system is neither stable nor causal for this particular area. So if I draw it again, so this is 1 upon 4. This is half, and this is the area, that is this annular ring. So for this particular annular ring, I can see that annular ring, then only it will be uh, into consideration when from 1 by 4. Let me just change the colors. The 1 by 2 will have this kind of nature, inward nature, and 1 by 4 ROC will have outward nature. So then only at that particular time this common area will be generated. Now at this particular condition we can see that ROC does not include the unit circle. Therefore this is not stable. Not stable. That means they have written neither stable. Now we have to consider the causality part. Now if half has the inward nature ROC, that means it has got some left side component in the time domain. That means this is not causal 2. That means the condition written over here at S1 and S3, these two are correct. Therefore, the option C, that both S1 and S3 correct, this one is okay. Okay, so with this we have solved 10 to 11 questions on this particular topic. So if you have any queries regarding the question that we have covered over here, so you can ask. And have you graded already for the quiz 1 and quiz 2?
Grading is done, sir, for quiz 1 and quiz 2.
Okay, so if you have any question for quiz, the questions that were there in quiz 1 and quiz 2. So if you have any confusions regarding, like if you have marked something and there was a mistake happened, so you can just tell me, I can solve the questions for quiz 1 and quiz 2 also. If you have any queries regarding the questions that were there.
Sir, is it okay if I ask you the queries related to the quiz 1 and 2 in the next class?
That is fine. That is fine. So I
Okay.
will solve the question. So do one thing. I guess you have my mail ID. So
Yeah.
because otherwise do one thing in the NPTEL forum, you can just post your question that like in quiz 2 whatever problem you have. So on
Okay.
the next class, I will take those particular questions. Otherwise, solving the whole thing will unnecessarily kill the time. So you just post the question over there. I will put a solution over there, and as well as I will consider those things in the slides also. So
Okay,
uh,
sir.
so I will cover those questions in the live sessions also. Okay.
Okay,
So
sir. Thank
apart
you.
from, okay. So I guess there is no further questions. So let me stop recording.